Recent advancements in computer science robotics, abbreviated as cs.RO, are bridging the gap between algorithms and real-world robotic applications. 17 papers published on April 26, 2025 demonstrate significant progress in autonomy, bio-inspired systems, and multi-agent coordination. These developments are poised to transform industries including healthcare, manufacturing, and transportation through capable and efficient robotic systems. The field of computer science robotics focuses on developing algorithmic foundations for adaptive robotic systems. By combining perception, planning, and control capabilities, researchers are addressing key challenges such as simulation to reality transfer, under-actuation, and swarm coordination. Notable applications emerging from this research include underwater exploration vehicles and advanced autonomous driving systems. Bio-inspired under-actuated systems represent a major research theme, achieving efficiency through nature-inspired designs. Walid Ramez and colleagues demonstrated 6 degrees of freedom control for autonomous underwater vehicles using just 4 actuators, achieving 99% energy efficiency. Their hybrid feedback system enables centimeter-scale trajectory tracking, while control allocation methods significantly reduce computation overhead. Autonomous navigation research focuses on safety in dense and uncertain environments. Dianwei Chen's team developed a deep reinforcement learning approach for collision avoidance in autonomous vehicles. Meanwhile, Yogesh Kumar introduced the Dart Quadrator, featuring innovative dual stiffness capabilities that allow it to switch between rigid and flexible modes after collisions for stable flight in cluttered spaces. Multi-robot systems research emphasizes scalability without centralized control. Manuel Boulder's work enables swarm coordination in GS-denied environments like forests, while Zhangqi Wai integrated hierarchical temporal logic with convex optimization for complex task allocation. These approaches demonstrate how communication-less algorithms can maintain safety and coordination in distributed robotic systems. Dexterous manipulation research is bridging the gap between symbolic planning and physical execution. Jie Chen's team successfully synthesized 31 distinct grasp types with an 82.3% real-world success rate. Their template-based optimization approach generalizes across objects, supported by a massive dataset of 9.5 million synthetic grasps for training purposes. Key findings across these 17 studies reveal important unifying insights. Under-actuation research shows 6 degrees of freedom control is possible with minimal actuators. Resilient systems like the Dart Quadrator demonstrate collision recovery capabilities. Swarm coordination advances work with GSS, while grasp synthesis research shows promising real-world transfer potential. Methodological trends in these advances include adaptive hybrid feedback for control theory applications, deep reinforcement learning for collision avoidance by convex optimization for motion planning, and extensive use of synthetic data. The 9.5 million grasp dataset exemplifies how synthetic data generation supports real-world robotic learning applications. A seminal paper by Walid Ramez addresses under-actuated autonomous underwater vehicle control. The research solves 6 degrees of freedom control using just 4 fin actuators through analytic allocation and adaptive feedback. This breakthrough enables compact underwater robots for exploration, achieving 99% energy efficiency and validating 5 degrees of freedom control in real-world tests. Thixin Wan's important work on embodied AI systems identifies latency challenges with large language models and robotic agents. The paper proposes system-level optimization paradigms and provides a roadmap for scalable embodied AI deployment. Key findings highlight prompt explosion and self-correction bottlenecks that must be addressed for practical applications. Jie Chen's universal grasp synthesis research tackles the challenge of generalizing grasps across 31 taxonomy types. The solution combines template optimization with contact-aware control, effectively bridging symbolic planning and physical execution. With an 82.3% real-world success rate and a dataset of 9.5 million grasps, this work significantly advances robotic manipulation capabilities. Future directions for computer science robotics include hardware-software co-design tailored to actuator constraints, self-supervised learning to reduce dependence on curated datasets, ethical frameworks for autonomous swarm safety, and continued efforts to overcome simulation to reality gaps in embodied AI systems. 3 key takeaways emerge from the April 26, 2025 research. First, bio-inspired design enables efficient under-actuation, as demonstrated by Ramez underwater vehicle control. Second, scalability requires communication-less coordination approaches like Boulder's swarm algorithms. Third, successful real-world transfer depends on synthetic data generation, exemplified by Chen's graph synthesis work. This research digest was synthesized through AI-assisted analysis of 17 ArXiv preprint server papers using advanced language models with careful human oversight to ensure technical accuracy and coherence. The visual presentation follows established text-to-slide conversion guidelines for optimal information delivery. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from ArXiv preprint server. Neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.